one of the variables is the position of the card pole in the horizontal space. One of them is the angle of the pole. One of them is the speed of the cart. One of them is the speed of the pole. And it doesn't matter what it is. And then what we'll do is we'll have another. So, actually probably that's just too early. So Q will give you a left and a right, and the Q values for each of those. What we need to do then is, so we want to evaluate, what the best action is using Q. The Q network. I'm going to need. So assuming batch is S plus 1. This is your future state. What this is saying is, okay, we want. So what we want is the action that maximizes your Q value. In this scenario, we want the action that maximizes Q. So we can do a tf.arg max, your Q result.
I think you just put dimension -1, right?
X.
No, it's dimension.
Dimension?
Yeah.
So, best action. In this scenario, it's choosing the action, which is position 1, that maximizes this array, and then you feed it into, and then you use that to choose your. So
you can play it up all the time. So
yeah, so your Qt result, let me just print it out. In this scenario, your best action was that. So you take 1 as your best action, and then you use that to choose your Q value, and because it's 1, you end up using that one. If this value was like 9, then the best action would be 0.
So are you saying for double DQN, you end up choosing the second value in QT? Is that what you're saying?
No, you use 1 to evaluate what the best action is.
Yep.
And you take that best action, and you choose the value from the other network.
But that's normal DQN.
No. Normal DQN is you actually just use the maximum value that comes out of your target network.
And
So it just uses the max out of your target network.
yeah.
Whereas
So how would you modify it over there? Like how would you
the
change?
code,
Yeah, the code. Like if you would complete the to-do section.
it is in the next. It is already there in the next one.
Oh, I see.
So how you would do it is feed your next state into your queue network, pick the argmax, that's your best action, right? I didn't want to use TensorFlow gather, so I just changed it to one hot, which means I can just simply do a modification to pick the best queue value. So the difference between this and that is, this is your, one is choosing the maximum value out of Qt, and the other one is actually use another network for the action, and then.
So because you have two networks, I think I missed that part. Anyway, sorry, I don't hold you up.
No, that's okay.
You mean two networks in the sense that you have the frozen one and the
Yes.
currently
So
updated.
the T target is always frozen.
Right.
But you you update that after every training session, right?
After 10,000 or whatever you define. Yeah. So it's like you hold one stable, you train the other one that moves, and then you go, oh, and then you start training again.
Yeah.
So the one that's frozen is always target network.
Okay. I'll need to take it.
It's probably a little bit dense. And the multiplication is, when you have one hot, if you do a multiplication, it ends up just keeping the node that you took. How do I best describe that? Let's say you have one. What? This thing died. Oh, that's the wrong one. Alright. Let's say you've got an array of 0 to 3, and you define b equals to array. 0, 0, 1, 0. Right. What ends up happening is it ends up being a selection, and you just keep the value that you indexed. Does that make sense from a selection perspective? When you do a matrix multiplication, if all of them are zeros, in fact this is not even a matrix, you get the point.
Mm-hmm.
When you do A times B, you end up going A, when you do A times B, what happens is you have 0 times 0, 1 times 0, 2 times 1, 3 times 0. And so the result is your one hot selection. I feel like this is a little bit intense or too much. Yeah. Shall we move on to the next one? I think the next one is
Would you
slightly.
show me the right
Yeah.
code again?
Sorry?
Will you show me the right
Right code?
Yeah.
I haven't copied that across. So the right code is find out what the best action is, usually 0 or 1. And I converted to one hot for convenience and just did a matrix multiplication. It's in your next exercise anyway, so you don't have to write it down. Yeah. Yeah. Shall we move on?
Yeah,
Yeah.
absolutely.
Alright, so what's a dueling DQN? I find this one to be quite fascinating. So a normal DQN, you've got a Q network, you feed it pixels, it goes through convolutions, and then you'll have a dense layer at the end, and it will output a list of Q values. So you know, if you've got left and right, then that's 2 Q values. In the case of Atari, there's like, I don't know, 10 or something, or maybe a little bit more. What dueling did is, instead of just outputting Q value, it first calculate a state value as well as an advantage for each action. And then they do an addition to achieve a Q value. Does that make sense? Yeah? The intuition I get from it is, in this scenario, when you're actually just outputting the Q values and then you're doing a neural network training, you're actually training one action at a time. And that means, you know, if you're training this action, that action is not really getting much training at all. What was interesting is, because of this addition, you're constantly training what the value of your state is, as well as that. And there's a little bit more than just addition happening here, which ends up training all of this at the same time, regardless of which action you've taken. And the next slide is where what I find the most interesting. So when they train the neural networks.
Just a quick question. Could you just remind me what advantage is? I haven't looked at this for a while.
Think of it as the Q value, or you know, the value of an action.
Right.
So
it's using essentially a shared representation to generate both the quality and the action value.
Yeah.
The policy and the quality.
Yeah,
right.
yeah.
That makes
Both the
sense.
action value and the quality of your state.
So, if you were to go back to the carpool example and try and create it, so in the end, at least in the top one, we know that Q only has 2 values. Right?
Yes, that's right.
So with bottom one, like the last Q, I'm using is 2 values again, but the advantage and the value function, how many?
So there will be one value because there's one state. The advantage will be 2 because one per action, and the Q will end up being 2.
How do you enforce that? So essentially, you're just going to have several units that are assigned to advantage and several that are assigned to the value. How do you somehow sort of ensure that that's what they're actually doing? Surely that's somehow encoded in the...
So if you look at this and you're like, oh, if I'm training this,
Exactly.
This is going to go down and this is going to go up, and you end up with 0. How's that even going to work, right? The technique they found to stabilize it is actually a little bit more complicated than just V plus A. It ends up V plus A minus the mean of A, and that actually helped to stabilize it.
So there's nothing actually. So the Q, you know, it actually gets connected onto the Y value, right, when you're training it.
Yep.
So there's nothing connecting the A or the B's onto any external thing to
No.
train it.
No, this is the only feedback.
So they're pretty much free to move.
Yeah, they are. What's interesting is by doing a minus mean on the A, they managed to stabilize it, which is quite interesting. Yeah.
Like minus mean in this batch normalization sense, or
Just a simple mean of
Simple
all your A
mean.
values. Yeah. I find this really fascinating because after they've trained it, they started looking at, given a state, where are the actions activating? And so, for example, in a scenario where the game where you're driving a car on the road and you have to avoid obstacles, right? For the value network, it's actually interested in the number here as a score, and also it's interested in up ahead where the road is targeting. And for the advantage, the action, it's not interested in anything at all. But when you get to a state where you actually have cars in front of you, the value network is interested in the road ahead, the score, and also a little bit about the car in front because you can actually hit it. And also for action, it's actually also interested in that. Which is quite fascinating. And I look at this, I'm like, wow, that's really cool. Yeah. So they found that or the intuition was that it actually eventually learns which actions are actually useful and which actions are not, when they've architected that way.
Sorry, just one last question on this connecting the carpool thing. So suppose we have 20 actions, right?
Yep.
Is the value, regardless of the number of actions, always going to be 1?
Yep.
And
Yep.
the advantage will just be for the number of actions?
Yes.
Yeah.
Yes.
Okay.
What's also fascinating about this is when we go into actor critic and all of that stuff, the V's are a concept that gets used a lot as well.
Same with advantage, actually.
Yeah. Okay. From an exercise perspective, I think this is an interesting one to do. So the normal Q value is just that, right? But in this scenario, we actually have an advantage, where the advantage is Q minus V. In simple means, you calculate the V and you calculate the advantage. You do a V plus A, and then you do a mean of A minus from that. Do you guys want to have a go at doing that at all, or just want to go straight to answers?
How much time do we have tonight?
We only have 3 hours, so
So only an hour and a half left.
Yeah.
So
Yeah.
I think if we go straight
You
to
try
answers,
to-
Okay, straight to answers.
run everything and see how it works.
Okay. I need to copy it from somewhere. I don't think I have the answers here.
holy shit. man.
Actually,
Wow, that's impressive.
why don't we, do you want to just do it here? Should we try it? And this, we define a V layer equals tf.keras.layers.
That's a good one.
Equals to 1. So in this scenario, our normal output becomes your advantage. V equals to self.v. Our Q value becomes V plus A minus TF dot reduce I needed to go access it. One and keep. Let's do some debugging as well.
Oh yeah. So what exactly is advantage? Like how's it different from Q? Pretty much Ben's question.
Think of it as essentially Q, or the additional value on top of your state value.
Because I think of it as like V minus Q. So like
Yes, it is.
oh yeah,
The
sorry,
other way, the other way around.
Yeah.
The other way around.
If you know what V is, that is.
Yeah.
Yeah.
Q, it's the advantage of that Q action on top of the value. I don't even know how to explain it.
So your state action pairs your Q value. That's like that's the value of being in that specific state for that specific action. And then your V is just your value for being in that current state, and you just minus it, and that's the new metric called advantage.
Yeah. So I've got a problem here. What's the error? Unsupported type. So, if the advantage is this, then our mean is that, which is about right. So the implementation is quite straightforward, actually. That's all it is. You define your V layer.
Oh yeah.
You feed the output of your first dense layer into V. You also feed the output of that dense layer into your advantage. Your advantage is 2, your V is 1, and you do a addition and minus the mean.
So you were saying that the reason that it's important to have these two things was this reduced mean part.
Yeah, that actually makes all the difference. They've tried variations where they use the max instead.
Try everything, right?
Yeah. I think this is the simpler one, and yeah.
So sorry, are they? I'm just trying to follow this. Is there so are you using where does the dueling part come in? So I get it's your Q value minus your Q minus V.
Dueling is essentially having two arms come out and then converge.
Oh, yeah.
Where the advantage and the value.
Are you using separate neural networks for? Sorry, yeah.
It's one neural net that splits into two
Yeah.
and then converges.
Yeah. Okay. Yeah.
And is there some sense in which what the V and the A are doing is adversarial? Or is it, like, why dueling? Is there like a tension between those two goals?
I don't know, actually, behind the naming of it. I think dual is just simply the two arms of it. I think it takes inspiration from Actor Critic, to be honest.
Yeah, it
Where-
seems so similar to.
Yeah, where Actor Critic, you actually have it two separately, and you don't ever converge. You're using one to estimate your value, your state value, and then using the other for your action probabilities.
I was thinking that, or like, yeah.
Yeah, I think so. This was in 2015 or 2016, so it's roughly similar times. Yeah.
What happens when you take out the mean?
When you take out the V,
The mean.
the mean, it becomes really unstable.
So
you wanna see it?
even in a simple case like this.
Yeah, it was interesting. So let's take it out. Let's just run it for 5 iterations.
It's like removing the intersection.
Oh, one thing to note is the difference between. So with normal Q learning and double Q, I run it for 100 iterations on the couple. It tends to average to about 30 something to 40. What do you call it? Mean reward over 100 episodes, where I just finish it at 175 steps. For for dueling DQN, it actually ends up at about 100.
What was it before? It was
It's about
40
35.
something.
So,
but hang on, so this was after you took out the.
oh no, this is
this is
stats that I've run at home. Yeah.
Okay.
When I saw this, I was like, oh, okay. Interesting that even for small scenarios.
So this is, you say that this is stronger than what was that one? Double DQN?
Definitely. Double didn't seem to make any
Oh, so double DQ was a 30. Oh, it didn't make a difference with the.
only like a few.
I see.
You know, because it's average over 100, we can't say
Sure,
much.
yeah.
Yeah.
Okay.
Do you think it's also worth stressing the point that, like, going back to right at the start of your lecture, well, where Deepmind showed their ablation test, that like certain implementations of DeepQN,
Oh yeah, it didn't
Well-
have as much of an impact.
yeah, and like for Kite there'll be some that do better than others.
Yeah, probably.
Yeah.
Probably.
Yeah.
Where's the ablation? Yeah, so when they took out this thing, so what they did was they ran rainbow DQN with all the different variations combined, and then they slowly tried taking out one of them.
What's rainbow?
So the rainbow is a DQN version which contains the original. It has the double, it has the prioritized experience replay, it has dueling, it has multi-step, noise endurance, and distribution DQN, all combined, all of the concepts. And then they tried, what happens if we remove double? And the purple one, double, didn't seem to make much difference. The dueling one only made minor difference when they took it out. The more interesting one is multi-step and prioritized experience replay, which when they took it out, it was a much sharper drop in terms of performance. What's interesting is even though we took out the V or the mean, it seems to be going well. When I tried it yesterday, it wasn't the case. Not sure what's going on there. Yeah.
I mean, if the normal neural nets
Let's run it again, see what's going on. Shall we?
I think,
Yeah.
yeah.
Okay, so multi-step. it's also pretty much extending on existing concepts, but just applying it to DQN. So instead of, there are different variations. So instead of just using the reward from your next state, he actually looks further, down the stack and go, if I want 2-step or 3-step or 4 to 5 step further, and actually propagate that reward back as my Q learning reward.
So could you say it's similar to like Monte Carlo? Is it more like going down
Also,
Monte Carlo?
Monte Carlo is, you go all the way to
It's
the end and you
step.
propagate it back.
Yeah.
And so the actual multi-step implementation that Deepmind ended up doing was they added a sort of a sigma variable where if sigma is 0, it used it looked at all of the actions and did some kind of averaging or whatever. But if sigma was 1, it uses the action that you actually took.
Can you explain the notation of those diagrams? Like which one's a state and which one's an action?
The arrow is the action. Oh, sorry, no. The red, the black dot is the action. And this big circle, empty white circle, is a state.
Mm-hmm.
If you go back to the first out of 4.
Yep.
4 step.
This one.
Yeah. So are you saying that before you take the Bellman equation, what you end up doing is you look at 4 few. So in the cart4 case, right, you end up looking at 2 to the power 4 cases. So basically,
No.
In this scenario,
yeah,
you're just playing a rollout.
yeah,
Take random samples, but keep track of every action you've taken and every reward.
yeah,
When you store it, for the very first state and action pair, when you store it, the reward is actually, this reward, immediate reward, this reward discounted all the way back. So it's essentially discounting all your cumulative rewards all the way back to here, and use that as your
like instead of RT plus gamma times Q.
yeah.
So instead of the Q, you're using the Q like
You're using the Q here instead.
Q in four
Yeah.
stages later.
Yeah,
Right,
yeah.
okay. But you're taking the maximum action at each.
And
Right.
you because you've taken all these actions, you actually you're propagating all the rewards back as well. So the idea is, if I was in this state, I'm learning that given this state, I can, and going down this path, I learn it. I gain all this much reward and potentially future rewards.
Right. So the Q is applied only at the after 4
Yeah.
stages. Okay.
It's safe to say vanilla DeepQN was just one step look ahead, yeah?
Yeah.
So that I think that's the important thing to take away from this is that
Yeah, essentially that's that. However, what Deepmind did was actually like combining, averaging all your future Q values with that. And if sigma was 1, then it's like this. But if sigma is 0.5, then it will do 0.5 of this reward value, and then 0.5 of averaging all your possible Q values.
Why is the 4-step Q? I mean, what is the combination between the expected sunset and free back up?
Why did they combine it?
Yeah, I mean, what's good with expected sarsa and then what's good in the free back up that they sort of mix together? Because that's how I'm looking at it.
This one is mainly, at the end of 4 steps, you actually start considering all your options. Whereas this one is just.
So 4-step expected is better than the sarsa because you're probably looking at more stuff. That makes sense. 4-step tree back up, you sort of look at more actions.
Yeah.
Because you have more data.
Yeah.
So why did the 4-step Q, the rightmost, you sort of look at less stuff? That's better, right?
I didn't. So what? In looking at the paper, I actually didn't see any comparison of stats.
Okay.
And when I implemented it, to be honest, I ended up